Well, let's start. And yes, thanks first of all to the organizers for putting up this conference and for giving me an opportunity to share some of our work with you today. And so yeah, this is a work on experimental quantum key distribution certified by Bell's theorem. And this is a work that we have. There's really a collaboration from several teams. So as you can see, I think we are about 15 people on it. This includes a experimental team from Oxford, as well as theory people from Lausanne, Zurich, Geneva, and ourselves, Nicolas Sangwa and myself, from Paris. So yeah, so what I would like to talk about today is probably a little bit different than most of the talks that you will hear at this conference. So I hope you enjoy it, nevertheless. And so you can also find the details here. And I should mention it's been published in Nature, and there are also 2 other works that are related that have those numbers there. So maybe to give some context, maybe you're just wondering, okay, what is quantum key distribution about? And so just very quickly, you at least heard of the recent Nobel Prize that was awarded to Alain Aspect, John Clauser, and Anton Zeilinger just a few weeks ago. And it was awarded for their experimental work with entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science. And so if you are curious to find out more about this, maybe you went to look at the scientific background put together by the Nobel Committee. And it mentions highlights of the development that has taken place over 40 years. Some of these experiments were done really 40 years ago. And that tells how this relates both to fundamental discoveries in quantum physics, as well as have direct relevance to practical applications. And the application that is mentioned in this document is actually quantum cryptography. So if you wonder how quantum cryptography is related to Bell inequalities, you are at the right place to learn more about it, because this is exactly the topic of our work. So without further ado, let's have a look at what a typical cryptographic task is about. And so here we have Alice and Bob, 2 parties that are distant. And a typical cryptographic task is to say that maybe Alice holds a string M, a string of bits, just a message. And maybe she has also additional information, maybe some K. And Bob only has K. And maybe what Ali wants to do is to actually send the M to Bob as well. So how could she do that? Knowing that they are at a distance from each other and they cannot meet. So she needs to send a message. And so one way to do that would be for her to actually take this string M and K and take the XOR of them and compute a new string S and send it over to Bob over a channel. And then if she does this, well, Bob will actually be able to recover the message M by taking the XOR of this message S with the string K that he has here. All right. So that would be one way to send a message, for Alice to send a message to Bob. And you might be wondering why do it this way rather than just send, for instance, M over to the channel. And the reason is that this very specific way to send a message has very good properties with regard to secrecy. And in particular, if we now consider that truly Alice is on her side, Bob is on his side, they both have maybe labs or homes that they know what's going on here, but outside is an environment that they don't control, and in which there could be an adversary here. And so the question is, well, if they use this encoding to send a message, the adversary only has access to the message S here, but doesn't have access to K. And so what information theory tells us is that having access only to S is not sufficient to gain any information on the message M. when things are encoded this way. And so this particle scheme is known as the one-time pad, and it's actually the only encryption scheme that is proven to be secure. And so it requires another string k that we'll just know as a key to encode the information. And so we see that secret or secure communication will basically amounts to having distant parties share a key k. And once they have this, then they are able to communicate securely. So this is what we'll be interested here, is the question of how to create a key between distant parties. And so this is what we call key distribution. And we could imagine, at first, we could just say, okay, let's try to create a key. And so we have Alice and Bob in their labs, and there's the channel in the middle, and maybe there's a protocol that they can follow, send some information back and forth, so that in the end they would have a key. Ka would be the result of this process for Alice, Kb would be the result of Bob's process. And ideally, those keys, of course, should be identical, like here, and they should also be secret, which means that nobody in the middle should be able to have a copy, hold a copy of these. So if you just think about it a little bit, you should be able to convince yourself that such a protocol does not exist. It's not possible to create a key at a distance, because if such a protocol existed, then an adversary in the middle could play it with respect to Alice on one side and with respect to Bob on the other side, and hold a copy of the key that they obtained. And therefore, if such a protocol exists, it is not secure. So this is a typical attack of cryptography called the man-in-the-middle attack. And what this tells us is that we, in order to create a key, or for any secure communication to start with, there's a need for an initial secret, K0, that will be first shared by Alice and Bob in the start of everything. And in fact, you can show that this is sufficient then to authenticate communication. And so the real deal here is to know that,
recording stopped.
Starting from a key shared by Alice and Bob, how is it possible for them to expand this key, make it longer, in order to use it in various tasks? And so this problem was analyzed in computer science, and solutions were found, and this is what we use nowadays whenever we communicate online. And current solutions, they rely basically on computational assumptions. So since it's not possible to really do this without further assumptions, then they assume that, well, some operations are just too complicated to be done efficiently by an adversary. So even if he can listen to everything, we just assume that he's not able to perform those computations, and this provides some security. But the problem with that is that existing protocols rely on difficulty of problems such as the factoring problem, factoring a large number into factors, integer factors. And it is known today that, well, since 1995 and the emergence of discovery of Shor's algorithm, it is known that that we have a quantum computer. This would be a task that is doable efficiently on a quantum computer. And so, of course, we don't have a full quantum computer yet, but, well, efforts are being pursued in the world. And just to give you an idea of where things are at the moment, companies like IBM have worked on systems that are able to they could make larger and larger, and currently there are about 400 qubits, noisy qubits, but still at their disposal. And current estimates are saying that, well, actually it would be possible to factor what is considered a difficult problem, a 2000-bit RSA key, with a quantum computer with between 10,000 and 20 million, which is very large still, number of qubits. And so we are not there yet, but somehow we are getting there. So we can really think about, okay, whether we want to find another another kind of protocols that would be resistant even in 10 years or 20 years to come. And well, if those classical protocol will break down, quantum theory actually provides also a solution to that. And this is what is known as quantum key distribution. And so how this works, or the idea behind that, is that if two parties, or two Alice and Bobs, share a maximally entangled 2-qubit state, well, this quantum state has very interesting properties. And in particular, the pure state is unentangled or uncorrelated to anything else. And at the same time, the outcomes of a measurement on a single state locally are fully random. It's not possible to predict what will be the outcome of, say, a sigma X or sigma Z measurement. So this is perfect. It's like unpredictable by an adversary. But at the same time, the person holding the other half of the singlet is able to obtain results that are fully correlated if that person performs the same measurement. And so this is exactly what we need for a private key, something fully correlated but unpredictable to any third party. And so based on this principle, quantum key distribution was developed over the years, and basically existing protocols relied on a number of assumptions, which is really small. We can just list them here. And so basically there are 5 assumptions. The assumptions are that quantum theory is correct. Then that the assumptions that, well, so Alice and Bob each have a lab, and of course no information should exit the lab, otherwise the security is lost. Then we need to be able here to choose between performing, say, a sigma X or a sigma Z measurement in a way that is independent, that cannot be controlled by an adversary. So we need truly random numbers, and then the post-processing, the classical post-processing must be done in a trusted way. And also the quantum devices, say the measurement operators that are realized here must be the one that we want. So in particular, that means that the devices must be well calibrated, trusted, and they must maintain perfect calibration. Basically, when we say we want to do a sigma X measurement, this should be really a sigma X, not something else. And under these assumptions, then it's actually possible to obtain really proven information-theoretic security, meaning without any assumption on the computational power of an adversary. Meaning here an adversary could do whatever it wants, as long as anything allowed by nature or by quantum theory. So that's all interesting, but the problem with that is that in practice, because these protocols have been realized over the past years, and you can even buy commercial devices. But the problem is that it's really, really hard to guarantee that a quantum measurement here is precisely what one wants to do. And in particular, any deviation opens a loophole, opens a way for an attack by the adversary and breaks the security potentially. So this was realized, and well, there are several solutions to that are possible. And one way is to just find, every time an issue is found, to find a countermeasure and a patch and go on, as is often done in security context, when there's nothing better that can be done, really. So that's one possibility. Another is to just go and try to really model the actual device fully from a theoretical point of view and try to find a security proof there. But this is just really impractical, because when you think about it, even just a photon detector, this is already a many-body system, and I think nobody here has the pretension to know fully how to describe an arbitrary manipulated system. So this kind of very tricky. And the third option that has been pursued and that we'll be interested here is to basically, on the contrary, try to lower the amount of modeling that is involved at the level of that theory to make sure that it can match what happens experimentally, sorry. And so what this means is essentially just look at all the devices as black boxes with some classical input and output, and just say, okay, we don't want to know what is really going on when we try to prove security. We just know that, well, when I press this button, then maybe the green light comes out, and we say this is the low level of description that we want to put on our devices. And when we do that, we're already able to get rid of this fifth assumption, that is the problematic one. And this is what is called, referred to by device-independent
recording in progress,
information processing in general. And so maybe that sounds like a fine idea, but how well, we'll have much less information about the system if we do something like this. So how can we still expect to find some level of security? And the key here is to basically play or test the Bell inequality. And this is what brings us back to Alain Aspect and others, because by playing a non-local game or Bell inequality, two parties are actually able to test in a black box scenario whether the system is close to a single state. And so this was formalized by Myers and Yao and others. And so what this means is that by playing this game, the players are able to know that they have essentially a singlet. And as we know, if they have a singlet, there should be some level of security because no third party can be correlated to them. So this was the basic intuition behind that, but it has been really formalized, and it's actually possible to evaluate and compute really what would be the uncertainty or the level of secrecy about the outcomes here as a function of this winning probability. So if we take this CHSH inequality or CHSH game, a score of 3/4, 75% is achievable classically, so it cannot have any secrecy. But quantum theory allows to go up to 85% of winning probability. And so we see that now it's possible to actually quantify as a function of the winning probability within this interval how much secrecy is there in the outcomes of the measurements inside the boxes. So, well, knowing this, we can try to now think about, okay, how could we leverage this to actually produce a key and to create a key between two parties. And so for this, we need to actually come up with a protocol, and there are two paths to a quantum key distribution protocol. One is quantum, is the generation of the data, and then there's a classical post-processing part that comes after that. I'll just briefly overview. So basically the data acquisition step involves an experiment of this type, where we would have, first, we need to create a state between Alice and Bob, an entangled state, herald it, and once the case, then Alice and Bob wants to basically isolate the system to make sure that nothing will come out at that moment. Once they are isolated, they can choose their measurement and perform the measurement and record the outcome. And there will be basically two type of measurement they can do. Either they will have test rounds, which basically are moments where we want to test this non-local game, this Bell inequality, because this is what will tell us about security. And then sometimes we'll also have generation rounds, meaning we'll try to make sure that Alice and Bob have outcomes that are as correlated as possible, because this is interesting to have just uh, um, more key. So basically, at the end of when repeating this at random over many rounds, then what the outcome of this will be that Alice and Bob will have each a string of settings, oops, and of outcomes that are just strings of bits or threads, and this is the result of the quantum measurements. And once this is done, then there will be need for a classical processing. And the reason is because, well, the outcomes may contain indeed some unpredictability, but they are also not fully unpredictable. And also, their outcomes will have errors, so they will not always be identical to each other. And so to have a key, we need to just correct all of this. And so that's why the first step is actually to do error correction, meaning that Alice will reveal information about her results to Bob to allow Bob to reconstruct a copy of Alice's outcomes. And this should be done by revealing as little information as possible, because all of this information will be available to the adversary. And after that, they'll need to check whether indeed the Bell inequality is violated strongly enough. Because if an adversary is there, then the violation will disappear. So that's the way of checking that no adversary is on the line. And then there will be privacy amplification, meaning concentration of the secrecy in the key, and at the end they need to still authenticate their communication, as we have seen, because without authentication there's no security. So with this, okay, let me just pass over the error correction and just mention maybe something about the security analysis. How can we analyze the security of such a protocol? And so there are different levels of security that one could be interested in. So in this context where an adversary has access to the channel, and basically we could imagine that at every round the adversary could be here and perform a measurement on what is going on. And if he does that, always the same measurement, we call that an individual attack. Or he could also do another measurement, but just an interaction each time. That would be a collective attack. But what we are really interested in is to basically obtain a key without enforcing any constraint on the adversary. That's the only case in which we can obtain information-theoretic security. And so this would be in the case of coherent attacks, which is what we'll be interested in and in this work. And so the secrecy then can be formalized. We can really quantify how secret the key is, and in the end, it will boil down to computing a smooth mean entropy. Maybe I'll just go over that so we can have a look at the setup and of the actual experiment. And so what does the setup look like? And this is the setup from the Oxford group. And so they have two strontium atoms that they hold in distinct traps, ion traps. And what they can do is they can entangle or they can let their ion emit a photon and stay entangled with the state of the atom. They can do that on both sides and capture the photon in the fiber. And what they use is then they use a Bell state measurement here in the middle to perform basically entanglement swapping. And when this is successful, then it announces, it heralds the entanglement between the two strontium atoms. And when this happens, then the protocol goes on, and basically they isolate the ion from the fiber by moving it away from the focus of the lens, and then they perform a measurement of the state of the strontium atom, and they do that on both sides. And by doing this, they're able to test Bell inequality between them. And so the CHC score they observe is about 2.68, which is really remarkable for this kind of setup. And the error in the same, when using the same basis on both sides, is about 1.5%, which is also extremely low. And so by looking at the security analysis with these parameters, we were able to show that well, there would be no key for any number of measurements that is less than 1 million. We would not be able to prove that. But starting from 1 million round, we would have actually the possibility to get a key with very good security. So security parameter of 10 to the minus 10. And so basically we went for a number round which was 1.5 million. And here's the result. So the data acquisition was 1.5 million rounds. And given the Bell inequality violation observed on those rounds, we're able to certify that there would be at least 400,000 secret bits. So bits that are really unpredictable by the adversary. Now, out of those, we still had to sacrifice 3/4 to allow Bob to correct all his own errors. And that left us with about a little bit short of 100,000 bits that were generated during the experiment. And this is still much larger than the 256 bits that were used and consumed by the protocol, and therefore demonstrating an expansion of the key. So here is, you have a picture of the key. Here, the key of Alice and the key of Bob. And we actually used it to encrypt an image of John Bell. And you can see here how a one-time protocol works. So the key is encoded, encodes this image. This is the message that is sent over a public channel, and that's what an adversary can see. But then Bob, with a copy of the key, is able to recover the initial picture. And so that was the actual data of the key. So with this, yeah, I just wanted to share that we we're able to expand the secret key with information-theoretic security and assuming only classical control over the devices, or device independently if you want. And so what's next would be to go to larger distances. Here the distance was about 2 meters between Alice and Bob, and to maybe also have quantum memories to avoid reopening the labs every time a new system needs to be distributed. And there are also a number of theoretical ways to improve things. And I'll just mention also that we are looking for enthusiastic and talented postdocs. So if anyone is interested to come and join us in Paris, he's happy to just we'll be happy to hear about him. And with this, I thank you all for your attention.
Thank you for the talk. Indeed, it's somewhat outside the field, so I'm wondering if there are questions. Hope there will be. Yes.
Thank you for a very nice talk. So I have a question. So how far is this technology which you have presented from relax commercialization, I would say? So what would be the practical cost of usage of this quantum network?
Yeah, thank you. That's a very good question. So there is a lot of effort being done throughout the world, and including in, especially in Europe, to basically build quantum networks over large distances. And this what I presented is really just the very first time that we are able to produce a key, and that's between on a very short distance, just a few meters. So obviously there's still a lot of work that needs to be done, especially experimentally, but also theoretically, to improve things and make things easier. And especially maybe we want to go towards photonic systems, maybe, because those are go well over fiber, so over longer distances. And there are efforts also in this direction. So I would say at the moment, at least this particular technology is more still at the level of first demonstrations, and will still take time, I think, to really come up with something that can be sold as a device. But that could be just a few years down the road, I would say, for the IQKD. But for really, say, the idea of having quantum networks, that would be the equivalent of what we have today as internet, but in a quantum version. That probably will take uh, more. I mean, there's much more work to do. Currently, the longest distances that are demonstrated are of the order of 1 kilometer, something like that. So that gives you, I guess, an idea of where things stand.
Great, thank you. Any further questions? Okay, again, thanks for this talk and also broad introduction. I think we got something what you about to convey. Let's thank the speaker once again.
Awesome. Thank you.
This concludes the session, and thanks for the audience being present in the end.